Hi everyone, this is Mrs. J, and today we're going to learn how to solve absolute value equations and inequalities. So first, I have a warm-up for you guys, so please pause the video and give it a try. All right, go ahead and take a look. So you'll notice here before I started graphing, I factored out the 2/3 within my absolute value, and then I just simplified it out front. So this is a form that makes it much easier for us to graph. So I can see my vertex is at 3, -5, and then my slope to the right is 2/3. And the slope to the left of my vertex would be the opposite, -2/3. Then to write this as a piecewise function, remember the x value of the vertex is always going to be that transition point. And everything to the right of your vertex, the absolute values are essentially not doing anything for this region because it was the values that were already positive. So notice they just turned into parentheses, and then I simplified. And then everything to the left of your vertex, everything inside the absolute value becomes opposite. So it becomes -x plus 3, and then again I just distribute and combine like terms. And then here's my piecewise function that describes this absolute value function. All right, so we're going to start by solving absolute value equations, and we will learn how to do this both graphically and algebraically, but we're going to start by solving by graphing. So for this, the first thing you're going to want to do is rewrite your function so one side is equal to 0. Once you've done that, you can graph that absolute value function on the other side, and then you're essentially just looking for the x-intercept or x-intercepts if they exist. Again, if your function is equal to 0, that means that you're looking for when the y value is 0, which again is our x-intercepts. So with these types of equations, there's 3 things that could happen. It is possible to get exactly one solution, and that will really just occur when the vertex is on your x-axis. It's also very common and possible to have 2 solutions. So here's our one solution. 2 solutions. Again, if your vertex is above the x-axis and your graph is facing down, or if your vertex is below and your graph is facing up. So 2 solutions is very common, but it is also possible to have no solution for these types of equations. So if your vertex is above and it's facing up, or if your vertex is below and it's facing down. So these are the 3 things, or 3 outcomes to look for these types of equations. All right, so let's give this first one a try. So here I'm going to set this equation equal to 0, so I'm going to subtract 5 from both sides. And then I'm going to graph this and then find the x-intercepts. So before I do that, I need to get it into the right form. So I'll simplify it a little bit. And so to graph this portion here, I'm looking at the left, my vertex is going to be at -3, 0. And then I can see that since my a value is 2, my slope to the right is 2. So the slope to the left is -2. And now that I've graphed it, I'm simply looking for the x-intercept, which is our vertex and is our only x-intercept. So our solution is x equals -3. Now, we could always go back and quickly plug this value in to make sure that it creates a valid equation, and in this case it does. So we are all done. All right, go ahead and try one on your own. Pause the video and hit play when you're ready to check. All right, go ahead and check here. So first I set my equation equal to 0, my vertex at -1, 4, my slope to the right is 1, slope to the left is -1. So you can clearly see our 2 x-intercepts at -5 and 3. Now, please note that when you're solving by graphing, you do need to make sure your graph is very accurate. So you need to be careful as you're following your slope to the right and left. And also, this method works fine when you have really nice answers that are nice integers. However, if you have a case where your x-intercept is something in between, you're really going to need to solve algebraically because we don't want to just estimate where that answer is. So graphing can be a good option. However, it's really only works when you have a really nice set of answers. So now we're going to talk about how to solve absolute value equations algebraically, which would probably be what I would choose to do if I were given the option. So when you're solving algebraically, the first thing you're going to want to do is isolate your absolute value expression. You'll see throughout the years we solve different types of equations. Isolating the main operation is going to be a really common first step. From there, we need to consider two cases that are happening. We need to consider the positive case of our absolute value and also the negative case. So then we're essentially going to take everything inside our absolute value and make it opposite. So from there, we actually have two separate equations that we have to solve separately. Now, once we solve each of those equations, we are going to check our solutions because it is possible with these to get what are called extraneous solutions, meaning all of the algebra you did is valid. It looks like we should have a correct answer, but it just does not work for our equation. So make sure you do check your solutions when you're solving algebraically. All right, let's give this first one a try together. So again, I'm going to start by isolating my absolute value expression. So I can start by adding 9 to both sides. And then I can divide both sides of my equation by 2. Make sure you're dividing everything by 2. And now that I'm done isolating, I'm going to create my two separate cases. So for the positive case, essentially the absolute value signs just disappear. Everything inside the absolute values we're assuming is already positive, so they're not really doing anything. And then for the negative case, everything inside your absolute value becomes opposite. So negative 5x minus 1 equals 2x plus 13. And then from here, we just solve each one separately. So 3x equals 12, x equals 4. Then for my negative case, it gives us 7x equals negative 14, so x equals negative 2. Again, we do want to go back and check to make sure both of those answers are valid. And you do need to show this step. So we're going to substitute our value in and show that the left side of our equation is equal to the right side. So when I do this, I have 2 times the absolute value of 21 minus 9 equals 33. So 42 minus 9 is 33. So 33 equals 33. So that is a valid statement. So x equals 4 is a solution. Now let's check x equals negative 2. So here, I'll go back to the original equation, or you can use any of these forms as well. If you use the original equation, you know that you haven't made a mistake yet. It's very possible that in one of these steps, maybe you made a mistake. So if possible, I would try to use that original equation. So here, 2 times the absolute value of negative 9 minus 9 equals 9. And here, remember, this will become positive 9, so 18 minus 9 is 9. So notice I'm not moving anything from the left to the right or anything like that. I'm just simplifying the right and left side separately and showing that they are equal to each other. So since both of our double checks came through, we do have 2 solutions to this equation. All right, let's try another one together. So here our absolute value is already isolated. So let's set up our 2 cases, our positive case and our negative case. So remember, everything inside your absolute value becomes opposite. So here we have 3x equals 18. And then here we have 5x equals negative 2. So now we need to check our solutions. So I'm going to substitute them into the original equation. So for x equals 6, we get a valid statement. So that is a solution. Now let's plug in negative 2/5. So here we have the absolute value of 48/5 equals negative 8/5 minus 40/5. So this gives us 48/5 equals negative 48/5. So this is not a true statement. So in this case, negative 2/5 is actually an extraneous solution. So that's why it is important that we check all of our answers. It is possible that we do all of our algebra correctly, but one of the solutions is not actually valid for our equation. All right, let's try another one together. So first here we need to isolate before we write our two cases. Now here, maybe you can stop and notice something. Here we have an absolute value of something equal to a negative number. So we know that the absolute value of anything should always equal a positive. So if you get to this point and you notice that your isolated absolute value is equal to a negative number, you can stop and just say no solution here. But let's say you didn't notice this and you continue solving. So let's say you set up your positive case and you set up your negative case and you solve. So here we have 4x equals negative 15, x equals negative 15/4, and then negative 4x equals negative 1, x equals 1/4. When you go to check your answers, both of them will end up being extraneous. So here we have negative 15 plus 7, so we have absolute value of negative 8 plus 10 equals 2. So 18 does not equal 2. And then for 1/4. So here we have absolute value of 8 plus 10 equals 2. And again, 18 does not equal 2. So both of our answers are extraneous. So whenever you see that, maybe you should go back and look here and say, oh yeah, look, my absolute value is equal to a negative. So this is no solution. So again, if you notice that from the get-go, you do not need to show all of this work. From this statement alone, you can just say no solution. But if you miss it, you should end up at the same conclusion with just a little bit more work. All right, so I have a couple for you to try on your own, so please pause the video and give them a shot. All right, go ahead and check your work. So here I have my isolated absolute value, and then I have my positive case and my negative case. We get two solutions, and I've shown my double check, and both are valid. So you do need to show this in your work. And again, we're just simplifying the left and the right side independently to show that they are equal or not equal. And then for part B, if you isolate your absolute value, the absolute value is equal to a negative. So at this point, you can stop and just say no solution. All right, so now that we know how to solve absolute value equations, we're going to now solve absolute value inequalities. And we'll start by doing this with graphing. So first, we're going to take that same first step. We're going to rewrite our inequality so one side is 0. And then we're going to graph the absolute value function that's on the other side. And we will look for those x-intercepts if they exist, just like when we are solving an equation. However, this time, since it's an inequality, our answers will probably be an interval of values. So from here, once we've determined the x-intercepts, we need to know if our solution should be everything above the x-axis. And if it says that your absolute value is greater than or greater than or equal to, your solution is the parts of your graph that are above the x-axis. And if your absolute value says less than or equal to, you're looking for the parts of your graph that are below. Sometimes this will occur as a single interval. Sometimes you're actually going to have two separate intervals in your answer, just depending on what your inequality looks like. All right, so let's give this one a try together. Here, one side of our inequality is already equal to 0, so now I just need to graph my inequality. So I am going to start by factoring the 3 out, and then I'll simplify it out front, so it's much easier to graph. So I have 3, -6 as my vertex, and I can see my a value is 3, so I'll use that to follow my slope to the right and left. Okay, so here I am able to determine that I have x-intercepts at 1 and 5, so this is a nice one. This is a problem that you can actually do by graphing. And now I just need to figure out, well, which portion of this is my actual answer. So here we're looking for the interval where our function is less than or equal to 0, meaning below or equal to our x-axis. So that's actually going to be this region here. So our solution is everything below the x-axis. So we're going to describe this interval. It's everything between 1 and 5. And it's going to include 1 and 5 because of the or equal to. So here our answer is 1 to 5. Or we could say 1 is less than or equal to x is less than or equal to 5. So we can do interval notation or that algebraic notation. All right, let's try another one together. This one, again, this side is already set to 0. So I can see that our vertex is at +2, -3. And my a value is 1. So our graph looks like this. So again, you need to be really accurate with your graph so you can make sure you can actually determine your correct x-intercepts. Now from here, this time our absolute value function, we're looking for when it is greater than 0, meaning above the x-axis. So we actually have 2 separate intervals where this is happening. We have the region of our graph to the left of -1, and we have the region of our graph to the right of 5. So our answer is actually going to have 2 intervals here. So that first interval will be -∞ to -1, and it's not inclusive because it's just greater than. And then we also have 5 to infinity, which is this portion on the right. Another way of writing this, we could just say x is less than -1 or x is greater than 5. So just these are 2 different ways, 2 different notations. This would be an algebraic notation, and this would be an interval notation. All right, so now I'm going to have you pause the video and try one on your own. All right, go ahead and check your work here. So make sure you set your inequality. So one side is 0 first, and then I graphed my absolute value function, and then I'm looking for the region that is below 0. So that's the region to the left of -8 or to the right of -2. So here's the interval notation or that algebraic notation. All right, so now we're going to learn how to solve these absolute value inequalities algebraically. Because just like our equations, if it's not a really nice inequality and we can't clearly see our x-intercepts, graphing's not really going to be an effective method. So when we solve algebraically, same first step, we're going to isolate our absolute value expression, and we're still going to write those 2 cases. We're going to write the positive case and the negative case. But from there, we need to be careful with whether our absolute value says less than or greater than. So if we see that our absolute value is less than our whatever our constant or expression is on the other side, we are going to separate the 2 cases with the word and. So less than gives us an and if our absolute value is greater than, we're going to separate the 2 cases with the word or. And we're actually going to write those words, and it's going to become extremely important. So after we solve our cases separately, we need to figure out what our answer actually is. So if the two cases are separated by the word and, we have to find the answers that overlap. We need to find the values that work for both, because and means it has to work for both. However, if our two cases are separated with the word or, there does not need to be overlap. So for these, most of the time you're going to have two separate intervals as your answer. So just like when we did graphing, sometimes our answer was that stuff in between and we had a single interval. And sometimes it was the portions on the outside where we had the two separate ones. So you need to be really careful when you're setting up your two cases with whether you have an and or an or. So less than is and, greater than is or. All right, let's give this one a try together. So we definitely need to remember that important first step of isolating our absolute value expression. Now here you'll see that we have less than, so this is going to be an and problem. So I'm just going to write the word and right in the middle before I do anything else so I don't forget. And now I can set up my two cases, one for the positive case and one for the negative case. Remember, everything inside becomes opposite, like this. And now I'm going to solve. So we have 4x is less than 24, x is less than 6, and here negative 4x is less than 8. And here, be careful, we're dividing by negative, so it becomes x is greater than negative 2. So again, all of these are ands. So now we need the region that is less than 6 and greater than negative 2. So if it helps you to visualize this on a number line, here's negative 2, here's 6. Again, we want everything that's less than 6 and greater than negative 2. So it's just going to be those numbers in between. So we have negative 2 to 6, not inclusive, or we can write it algebraically. Negative 2 is less than x is less than 6. So when you have that and, your answer is just going to be that single interval. We wouldn't want to write our answer as x is less than 6 and x is greater than negative 2 because we can be a little bit more concise with that. All right, let's try another one together. So let's start by isolating our absolute value. So I'm going to subtract 5 from both sides, and then I'm going to multiply both sides by 2. Okay, so for this one, we see that our absolute value is greater than 12. So this is going to be an or problem, which means we don't need to have overlap in our intervals. So we're going to still set up our two cases. Then we have negative 6x minus 3 is greater than or equal to 12. And now we solve. So 6x is greater than or equal to 9. X is greater than or equal to 3 halves. And it's or all the way down. So here, be careful, we are dividing by a negative, and then I'll simplify to negative 5 over 2. So again, since we have that or, we don't need any overlap, which, is good because we actually don't have any overlap in this case. So if you want to visualize what's going on here, here's 3 over 2, here's negative 5 halves. So it's the numbers that are greater than or equal to 3 over 2 or less than or equal to negative 5 halves. So you can see we actually have two separate intervals here. So we can write our answer in interval notation. So negative infinity to negative 5 halves, which is inclusive, or, so we use that union symbol, 3 halves to infinity. Or we could use that algebraic notation, x is less than or equal to negative 5 halves. And for this one, we would actually write the word or in our answer. And there you go. So again, just be really careful and notice if you're working with an or problem or an and problem. All right, let's try another one together. So let's take those first few steps and isolate. And then I'm going to divide both sides by 5. Okay, so here I'm going to note that this is an or problem because it is greater than or equal to. So we have our two cases, our positive case. Now you might notice something right off the bat here. We do have an upward facing absolute value function whose vertex is going to be on the x-axis, and we want to know when that function is greater than -6. So you might notice that right off the bat that this function is always going to be greater than or equal to -6. So maybe you have an idea of what to expect, but let's say we finish solving algebraically here. So we have 2x is greater than or equal to -34, so x is greater than or equal to -17. Or -2x is greater than or equal to 22, and x is less than or equal to -11. Now again, since it's an or problem, we do not need any overlap. So let's visualize what's happening here. Here's -17, and here's -11. So again, overlap is not necessary. If it's everything greater than or equal to -17 or less than or equal to -11, you can see that that is literally everything. So this inequality actually has all real numbers as its solution. So we could say this, or we could say x equals all real numbers. So this is kind of not as common case, but you can definitely expect that it will pop up every once in a while. So just be careful. Again, as long as you understand if you're working with an and or an or problem, you should be fine. If you need to visualize what your answer is on a number line, then definitely do it. All right, I've got one for you to try here on your own. So pause the video, give it a shot. All right, go ahead and check your work here. Be extra careful with this step. Notice here you are dividing by -8, so it actually becomes less than or equal to. Since it's less than, it's an and problem. So when you solve the two inequalities separately, you're looking for the overlap in answers, the stuff that works for both, which is the numbers between and including -17 and -11. All right, I have one last problem for you to try. So again, pause the video and give it a shot. All right, go ahead and check your answer here. So isolate, notice this is an or problem. So when you solve your two inequalities separately, you get x is greater than 28 or x is less than -20. So again, there doesn't need to be an overlap for an or problem. So we have two separate intervals, which you could write in interval or algebraic notation. All right, that is all for today's video. Thank you so much for watching.